Section: Introduction. In this section, we explore how large language models, LLMs, have excelled in various tasks that involve understanding and reasoning about extensive contexts. One common task is document question answering, where the model needs to comprehend a document and respond to questions or summarize the content. However, dealing with very long documents can be challenging for LLMs due to their context window limitations. To address this challenge, there is a growing interest in academia and industry to enhance LLM's ability to handle longer contexts effectively. Despite the progress made by LLM providers like OpenAI and Anthropic in developing models for processing lengthy texts, scaling these models to manage extended contexts remains a significant technical and financial challenge. Transformer-based LLMs, with their self-attention mechanism, face computational and memory overhead that grows quadratically with the sequence length. Tasks involving long contexts often require repeated processing of the same information, leading to additional latency and costs, as commercial LLMs charge based on the number of tokens processed. In response to the need for handling long contexts, our study introduces a new approach to tackle this challenge. We propose a method where context information is condensed offline through fine-tuning, enabling the model to provide accurate responses during inference with streamlined contextual representations. To explain our idea, consider an analogy. Think of an LLM as a student preparing for an exam, where we, the researchers, provide study materials and questions. Traditional methods allow the LLM full access to all materials during the exam, similar to an open book exam. In contrast, our approach is like a semi-closed book exam, where the LLM can only bring a cheat sheet. To excel in this scenario, the student must efficiently distill key information into the cheat sheet and effectively use it to answer questions during the exam. Our study focuses on two main questions: how to train a model to produce a concise yet informative representation of the original context, and how to enable the LLM to extract relevant details from this representation during inference. While existing research has explored context compression to distill text into compact representations, we concentrate on improving the LLM's ability to accurately interpret and utilize these compressed representations. By employing parameter-efficient fine-tuning directly on the compacted context without changing its content, we enhance the LLM's capability to extract and use information from these condensed representations. This approach enables us to extend the effective context window of a 4K Llama 2-7B model to handle up to 128K tokens, achieving state-of-the-art results that rival or surpass larger models while using significantly fewer tokens. This insight leads us to introduce LLoCO, a pipeline that combines context compression, retrieval, and parameter-efficient fine-tuning to enhance long document question answering efficiently and cost-effectively. Section Summary. In this section, we explore the challenges of processing long contexts with large language models, LLMs, and propose a novel approach to address this issue. By combining context compression and parameter-efficient fine-tuning, we extend the effective context window of a 4K Llama 2-7B model to handle up to 128K tokens, achieving superior performance with significantly fewer tokens and faster processing speed. Our proposed pipeline, LLoCO, integrates context compression, retrieval, and fine-tuning to enhance the efficiency and cost-effectiveness of long document question answering tasks. Section: Related work. In this section, we will discuss the related work that has been done in the field of long context language models, LLMs. Recently, there have been efforts to enhance the context window sizes of LLMs efficiently through continual pre-training or fine-tuning. One approach involves scaling the rotary position embeddings, ROP, to achieve longer contexts, while another method, called Mistral, uses sliding window attention to focus on only part of the tokens from the previous layer, reducing computation and enabling pre-training with longer contexts. However, storing the KV cache of longer contexts can slow down inference and require large GPU memory. Another related topic is context compression, which aims to train a general compressor to compress any input prompts. Various methods like GIST, autocompressor, and ICAE use different techniques to compress contexts into shorter embeddings. Additionally, there are approaches that compress the KV cache through eviction or quantization. However, these methods may lead to performance drops when the compression ratio is too high, especially for out-of-distribution texts. Our focus in this work is on extremely compressing in distribution documents of interest, achieving compression rates of up to 30 times. We also explore retrieval-augmented generation techniques, which improve LLM performance in tasks requiring knowledge integration. Parameter-efficient fine-tuning methods, like LoRa, freeze most model weights and update only a small subset for efficient fine-tuning of large models. Our proposed method involves a context encoder and an LLM decoder in the architecture. The context encoder compresses long contexts into a compact representation, which is then used as the system prompt for the LLM decoder. The user prompt is processed normally, and the LLM generates answers based on the summary embeddings and user prompts. We use AutoCompressor as the context compressor for our experiments, as it can compress long contexts effectively and achieve a high compression ratio. In summary, our work focuses on extreme compression of in-distribution documents, utilizing context encoders to enhance efficiency and effectiveness in generating responses. Section Summary. In this section, we explore related work in the field of extreme compression of in-distribution documents, context compression techniques like GIST and AutoCompressor, and the use of retrieval-augmented generation to enhance LLM performance. We also delve into parameter-efficient fine-tuning methods such as LoRa and introduce our proposed architecture, LLoCO, which utilizes a context encoder to compress long contexts into summary embeddings for efficient generation in LLMs. Our focus is on developing more performant and universal context encoders to enhance the efficiency and effectiveness of LLoCO in extreme compression scenarios. Section: Pipeline for Offline Context Learning. In this section, we present our pipeline for offline context learning, LLoCO. Our pipeline consists of three main stages: pre-processing, fine-tuning, and serving. We explain how we integrate this pipeline with an existing RAG system to enable retrieval-augmented document QA with compressed context. In the pre-processing stage, we typically chunk documents into passages, generate sentence embeddings for these passages, and index them. In LLoCO, we add a step where we use our context encoder to process the original documents. We divide the documents into chunks of 1536 tokens and pass them through the context encoder to get 50 summary embeddings for each chunk. During the fine-tuning stage, we group documents based on their type or the tasks users want to perform. We then perform parameter-efficient fine-tuning using a LoRa adapter. This involves using in-domain instruction pairs or generating data using self-instruct techniques or distillation from a more powerful model like GPT-4. In the serving stage, instead of retrieving actual passages, we retrieve compressed token embeddings of the passages. These embeddings are then used in the serving pipeline. We search for the corresponding LoRa adapter in the database and apply it to the decoder LLM. This incurs minimal overhead to the system cost. We can parallelize LoRa adapter serving and handle requests for documents associated with thousands of LoRa adapters on a single GPU. Our system assumes that all retrieved passages for a user query belong to the same document group, allowing us to use a single dedicated LoRa adapter. However, we can extend this to handle cases where passages span multiple document groups. In our experiments, we aim to evaluate LLoCO's effectiveness in understanding compressed long contexts, the preservation of essential information in summary embeddings, and the associated system costs. We use datasets dedicated to question-answering tasks and summarization tasks with long documents as contexts. We report different evaluation metrics for each dataset. We consider two base models in our study, Llama 2-7b4k with a context window of 4096 tokens and Llama 2-7b32k with an extended context window of 32,000 tokens. We fine-tune all LLoCO models on AutoCompressor, which is itself fine-tuned on Llama 2 to 7b. Section Summary. In this section, we present the pipeline for offline context learning, LLoCO, which comprises three main stages: pre-processing, fine-tuning, and serving. We introduce an additional pre-processing step in LLoCO that utilizes a context encoder to process original documents by dividing them into chunks and generating summary embeddings. During the fine-tuning stage, documents are segmented into groups and fine-tuned using a LoRa adapter, resulting in a fine-tuned LoRa adapter for each document group stored in a vector database. In the serving stage, instead of retrieving actual passages, LLoCO retrieves compressed token embeddings of passages and applies the corresponding LoRa adapter to the decoder LLM, allowing for minimal system cost overhead and potential parallelization of serving requests for documents associated with multiple LoRa adapters on a single GPU. Section: Long Document QA. In this section, we evaluate the effectiveness of LLoCO on long context datasets through various scenarios. We start with a scenario where we do not provide any documents to the LLM in the system prompt. Then, we move on to a scenario where we give the LLMs the ground truth document, truncating them if they exceed the context window limit. This scenario serves as our baseline. Next, we explore a scenario where we use retrieval as a standard baseline compression method. We divide each document into passages of 512 tokens and retrieve the top 5 passages using Contriever, concatenating them to form the context. We also consider a scenario where we employ AutoCompressor to compress the contexts into summary embeddings and prepend them to the LLM without in-domain fine-tuning. The AutoCompressor compresses 1536 tokens into 50 summary tokens, effectively creating a context window of around 128K tokens. Then, we introduce our proposed system, LLoCO, for long document question answering. For each dataset, we conduct instruction fine-tuning using question answering pairs from the training set. During both fine-tuning and inference, we prepend the summary embeddings of the corresponding ground truth document to the LLM. Our results, summarized in a table, show that while AutoCompressor's performance sometimes falls short of the baseline without context, LLoCO significantly outperforms the baseline on all datasets by a large margin using 30 times fewer tokens. Particularly, on the narrative QA dataset, LLoCO achieves an F1 score of 28.34 compared to 14.42 for the baseline, demonstrating the effectiveness of our approach. Furthermore, LLoCO excels on the narrative QA dataset, where the average document length exceeds the context window limit. By compressing the contexts into approximately 2,600 tokens on average, LLoCO fits the compressed representations within the context window limit, leveraging all available context and achieving impressive F1 scores. In an ablation study, we investigate how well LoRa fine-tuning works over original uncompressed context compared to LLoCO's approach. Fine-tuning in a compressed context proves to be as effective as fine-tuning in the original context, with LLoCO offering a faster and more cost-efficient solution for long document question answering tasks. Moreover, we explore the performance of LLoCO with combined fine-tuning on all training data. The combined fine-tuning surpasses baseline methods on most datasets, except for QM-SUM, where the summarization task prefers longer, more detailed answers. Overall, combined fine-tuning shows potential for knowledge transfer across different tasks, enhancing the LLM's ability to reason about long contexts and improve performance. Section Summary. In this section, we evaluate the effectiveness of various methods for long document question answering, including using AutoCompressor and our proposed system, LLoCO. By combining compression and fine-tuning, LLoCO outperforms the baseline on all datasets significantly while using fewer tokens. Additionally, our experiments show that fine-tuning in a compressed context with LLoCO is as effective as fine-tuning in the original context, making it a more practical and efficient solution for long document question answering tasks. Section: Evaluation on long bench. In this section, we assess our LLoCO model on the long bench dataset, which includes 6 subtasks. Our focus is on single doc QA, multi-doc QA, and summarization tasks, which are crucial for document question answering and summarization. We ensure that long bench has unique validation sets to prevent any data overlap with our training data, eliminating the risk of data leakage. To optimize LLoCO's performance, we use tailored LoRa adapters for each task category. For single doc tasks, we employ NQA LLoCO and Casper LLoCO, while for multi-doc tasks, we use a combined fine-tuned LLoCO. In the summarization tasks, we create a training dataset by merging QM-SUM and multi-news data, then fine-tune LLoCO on this combined set. Our evaluation shows that LLoCO outperforms the Llama 2 baseline on 5 out of 9 datasets, excelling particularly in multi-doc QA. However, it struggles with lengthy content generation in tasks like Gov Report. Despite some limitations, LLoCO performs better on average across all datasets compared to the baseline, demonstrating the effectiveness of our approach. We also investigate LLoCO's ability to retrieve information from different positions in a text of varying lengths using the needle in a haystack task. We test LLoCO on a long article from the narrative QA dataset as the haystack and evaluate its performance with fixed and random needles. Our model shows robust performance across different context sizes, outperforming the Llama 2 to 7B32K model. By continually fine-tuning LLoCO with a synthetic dataset for handling random needles, we significantly improve success rates, showcasing the effectiveness of our method in this task. Furthermore, we evaluate the inference latency improvements of LLoCO on GPUs and compare it with the Llama 2 to 7B baseline. Our model achieves speedups of up to 7.62 times on A100 and 7.19 times on A6000 GPUs, maintaining efficient generation for longer sequences. LLoCO can process sequences up to 128K tokens while achieving the baseline's latency for much shorter sequences. Additionally, we assess the fine-tuning throughput on the narrative QA dataset and find that LLoCO significantly outperforms the baseline in terms of efficiency and performance on both A100 and A6000 GPS.